Yes, good morning. Let me continue my class. In the yesterday's class, we have looked into the state of computing, and then we have looked into multiprocessors and multicomputers, multivectors and SIMD computers, then PRAM and VLSI models, and then architectural development tracks. Now, right. Yesterday we have looked into the various generation, the first generation, second generation, third generation and fourth generation, and we have looked into the technology that made it possible to move from one generation to the other generation, and then the number of users, the memory used, etc., the operating system and heterogeneity, etc., and then we have looked into the examples of each generation. Right. Now, let us go into the next one. Now, we will look into the elements of modern computers. Right. When I ask you what are the elements of the modern computer, then probably you would say the first thing that you are going to say is a computing problem. So, the computing problem is going to be the first element. The second one is going to be algorithms and data structures. So, this becomes the second component of a computer, algorithms and data structures. The third one is going to be the hardware resources. So, the third component is going to be the hardware resources. The fourth component is going to be the operating system. After operating system, the next one is going to be the system support softwares. Right. So, this is going to be the fifth component, the system support software, and the sixth component is going to be the compiler support. So, these are the major components of a modern computing system. The first one is the computing problems, then is the algorithms and the data structures, then comes the hardware design or resources, then is the operating system, then system software, system support softwares, and the last one is the compiler support. So, this all together forms the components of a modern computing system. Now, if I want to represent this in a pictorial one, now which component comes first? When you look into it, the first component obviously is going to be the hardware resources. Right. The first component is going to be the hardware resources. What is going to be the next resources out of this? Then it is going to be the operating system. The second component is going to be the operating system, which is going to encircle the hardware. Now, once when you have operating system, what is the next one that is going to be? One, it is simply going to be the supporting softwares, or sometimes I can call it as a application software. Right. The application software, probably this model you would have studied in a operating system. Right. Now, the question is, where does this compiler comes into picture, or before that where does this computing problem comes into picture? The major one that comes into picture is the computing problem, this one. So, computing problem. Right. Once when you have a computing problem, what is the next thing that you need to do? You need to decide what should be the algorithm that can be used to solve the problem and what should be the data structure that supports that defined algorithm, right. You are getting the point here. Once when you have a problem, now the solution to the problem is through a defined algorithm. You have to select an algorithm, and for that particular algorithm, whatever data structure supports best, that is going to be taken into consideration. Algorithms and data structures are going to be taken into consideration. Clear? Now, where does this algorithms and data structures refers to? Somewhere again they are going to be dependent on the application software, right. Now, does this both solves the problem of finding a solution? Probably to a certain extent, yes, but somewhere you want to talk to the hardware. So, that is where a hardware, if you want to talk to the hardware or if you want your computer to solve a problem for you, then you need to talk to your computer. The interface that allows you to talk to your computer is your high level language. So, once when you have decided the algorithm and the data structure, the next thing is you are going to decide the high level language. Now, once when you are familiar with a particular high level language based on the need of a problem, then you are going to look into this. Clear? So, this is how your modern computer architecture is all about. The first thing is you decide a computing problem. Once the problem is defined, which needs to be computed, then you would search for a suitable algorithm. Once the algorithm is selected or defined, then you would look for a suitable data structure that eases the job of this algorithm. Now, once this both is decided, then you will choose a high level language. Once the high level language is chosen, then automatically it is going to be given to the computer, wherein it takes the instructions and then executes. Clear? Now, all this is okay, but somewhere apart from this, one more issue comes into picture. That is nothing but performance evaluation, right. The performance evaluation comes into picture. So, these are the major components of a modern computer architecture. Now, the question arises is, why do you need to look into a performance evaluation? Obviously the performance evaluation is going to decide which algorithm to be used. You need to understand the problem. Based on the need of a problem, a particular algorithm has to be selected, representing data structures needs to be selected. Once this both has been properly selected and then executed using a supportive high level language, then automatically the performance issues are going to be addressed to a certain extent, because at the end of anything, the user is concerned more with the performance rather than the approach used. I, as an end user of a computer, I am not concerned with what is the hardware, what is the operating system, what is the application that is being used. I, as an end user, is only concerned with the performance. So, somewhere choosing all this is compelled for us to look into the performance evaluation, right. Now, if a particular system is not performing up to expected level, then obviously we will be compelled to change the approach or do something. Now, that is what we need to look into when analyzing a performance, right. This performance evaluation is what makes it for us to get evolved from one to the other. Now, when you see the progress that is being made across multiple technologies and everything, it is because of this performance requirement that has made it possible for a system to get itself evolved. Clear? So, these are the elements of a major computer component. Clear with this, right? Okay, then. Now, once when you are clear with this, now let us go to the classification of a computer architecture. Now, the question arises is, why do we need to look into the classification of a computer architecture? Because as I said, no, the architecture has evolved over a period of time, and the parameters that made it to get evolved needs to be known, right. in the evolution of computer architecture, we are going to look into classification. Right. For classification, what is the thing that they have used? So, they have simply used streaming. They have used a simple streaming of items. What are those items? These items could be either instructions or it could be data, right. For streaming of items, that streaming of item could be either a instruction or it could be a data. Now, using this instruction and data, a FLIMS has classified, has defined a taxonomy, has defined a classification. Now, he is using these two components, instruction and data, for classification, and this FLIMS classification was given in 1966, right. According to him, he uses these two items, instructions and data, for classification. And according to him, the first one is SISD. The second classification he says is SIMD. The third one is MISD. The fourth one is MIMD, right. So, it is single instruction, single data stream. The second one is single instruction, multiple data stream. The third one is multiple instruction and single data stream. The fourth one is multiple instruction and multiple data stream. So, this way the FLIMS has classified the computer architecture. So, it was classified in 1966. The two components that were used was the instruction and the data. Now, according to him, there are 4 classes. The first one is single instruction, single data, single instruction, multiple data, multiple instruction, single data, and multiple instructions and multiple data. So, these are the 4 classifications given by FLIMS. Because when you use a layered architecture for developing, then obviously that is the best suited one, because it allows flexibility in design, because the dependency on each layer is going to be less. Probably because of this less dependency, it offers a huge flexibility. Now, that is what this 6-layer architecture is all about. Right. This is a 6-layer architecture. The first layer is going to be the application one, then the second one is going to be programming environment, the second layer is going to be programming environment, the third one is going to be the language support, the third one is going to be the language support, the fourth one is going to be the communication model, the communication model that supports. The fifth one is going to be the address space, right, the address space, and the last one, the lower layer, is hardware architecture. Now, these are the 6 layers. Now, we call it as a development layer, right. The first one is at the bottom is going to be a hardware, then comes the address space, above that is going to be the communication models that supports. Once when you have a communication model, then you need a language support. Once the language support is available, then comes the programming environment, and then above the programming environment you will end up with developing a applications, right. Now, when you look into this the 4 layers are simply machine dependent. I mean to say that the architecture that needs to be is known to it, but whereas if you want this one 1 2 3 4, this one is machine independent, right. Now, if you want to develop an application, you do not need to know the hardware, you do not need to the address space, everything is not needed to be known to a programmer, because somewhere the operating system etc. are made such that a programmer does not needs to know about the internals. Clear? You got this? Similarly, if an application is going to, if a hardware is going to be designed, now he does not know for what application is going to be designed, but this hardware is going to be designed in such a way that it supports to a wide variety of applications. Now, that is where this development layer comes into the picture. At the bottom is going to be the hardware architecture, at the top is going to be the application layer. So, this is what we call it as a evolution of a computer architecture. It all started with the hardware, and then it ended with an application. So, this is going to have an influence on this address space. Again, a communication model is going to decide this communication, all three together is going to be with a language support. Upon that is going to be the programming environment, and then a application one. Now, this is what we call it as a developing environment, right. Now, if you port the same one onto a flow chart, simply if you put it onto a flow chart, then the first one is going to be a programmer. The application is going to be developed by a programmer. Now, what about the programming environment and the language support? It could be any source code, any language. It could be any source code. Once the source code is been ready, now what is the next thing that he needs to do? He looks for a compiler, right. Once the compiler is ready, then comes the object code. Once the object code is ready, then it is obviously the program is going to be executed, right. For an application, it is going to be a programmer, he develops a source code, from that it gets compiled. After compiling, an object file is going to be generated. So, this object file is going to be executed by a one. Clear? This is introduce parallelism. Can we introduce a parallelism in the source code? No, probably it may not be possible there, because the source code is simply a sequence of instructions. But if you introduce a parallelism, or if you introduce something into a compiler wherein it can pick up the instructions which are not dependent and then execute it concurrently, then it makes it possible for a parallel execution of the program. So, that is where this concurrent program execution comes into picture. Now, once this is ready, then obviously the concurrent object code is going to be developed, and then the program is going to be executed, right. Now, with this, so this is going to be the model that is being used. Clear with this? Right. Now, once when you are clear with the development layer, now let us go to the machine capabilities. Now, what do you mean by the word machine capabilities? The support that your programming language offers are going to be called as machine support capabilities. Right. The next thing that we are going to look is the machine support capabilities. What should be the first one? Machine support capabilities, and shall we look into the program behavior also, and machine supporting capabilities and programming behaviors. The first one is going to be a better hardware technology. The first one that needed is a better hardware technology. Now the next one is innovative architectural features, right? Innovative architectural features. The third one is effective resource management, effective resource management. The fourth one is the data structures. The fourth one is the data structures. Then comes the language efficiency. The language efficiency. The next comes the programmer skill. The programmer skill, and the last one is compiler technology. Right. Now these are the capabilities that needs to be addressed. The first one is a better hardware technology, obviously enhances the performance, innovation, innovative architectural features. This needs to be looked into so that you can somewhere minimize the resource needed and enhance the performance. The third one is effective resource management, then selecting a proper data structure, selecting a proper language which is efficient for that given particular problem, and then a very important parameter, is programmer's skill. So this plays a major role in deciding the program behavior. More emphasis is on this programmer's skill, and the last one is the compiler support. The compiler technology that supports or makes it easy for a program to be easily ported. So these are the one that needs to be looked into when you are talking about a system performance. So if you want to measure the system performance, or if you want your computer to be performing at an acceptable performance level, so somewhere all these issues needs to be addressed. So you as a programmer, your programming should be such that the instructions can be executed concurrently, the language support, the data structures that you have chosen, effective utilization of the resources, architectural features that you have used, and then the hardware technology support and the compiler technology support. All this makes it possible to achieve a performance, or I would say rather than a peak performance, right? Peak performance. Now the question is, how do you measure this performance? How do you measure this performance? Now this performance again is going to be measured as turn around time, TAT. I think you might have come across this word in the operating system, turnaround time. It is nothing but the total time that it takes for a processor to complete its execution at the instance the job is submitted till the job is completed. Now if you want a peak performance, somewhere all this needs to be addressed, and this peak performance is going to be measured using TAT, turnaround time. Now what about this turnaround time? This turnaround time could be of a memory, it could be for a disk access, it could be for memory, it could be for disk access, it could be a compilation time, it could be for compilation time, or it could be the operating system overheads, or it could be the CPU time, right. Now, if you are able, if you want to increase the performance, somewhere you need to look into all these issues. It could be the CPU time, or it could be the hover rate that are involved because of operating system, it could be the compilation time, it could be the disk access time, or it could be the memory access time, right, or even it could be a input output access time. Now, if you are able to address all these issues in a much better way, then automatically you are going to reduce the turnaround time. Once the turnaround time is reduced, then obviously we say a performance is going to be peaked, right. So, likewise these are some of the attributes that needs to be looked into, some of the attributes that needs to be looked into when you decide the performance of a particular architecture. Clear with this? Right? Okay then. Now, for measuring this, there are some parameters, such parameters we are going to call it as clock time, clock rate, or CPI, clock cycles per instruction, CPI, cycles per instruction, or clock rate, CR, or cycle time, CT. Likewise, you have got these parameters. Now, using these parameters, we are going to compute the performance factors, because your computer, everything is going to be measured in the number of clock cycles that it takes. For example, an instruction, for an instruction to complete its execution, it has got a defined clock cycles. For a memory access, it has got a clock cycles. For input output operation, it has got a clock cycles. Now, if you reduce the total clock cycles that are needed, then automatically you are going to enhance the performance, right. So, in the next class, we are going to look into the parameters that needs to be considered and the metric that are being used to measure the performance, and then we will try to derive a small formula which gives us the relation between the system attributes which contributes to the system performance. Clear? Again, these attributes could be either implicit or explicit, but whatever may be the thing, whether it is implicit or explicit, we are going to look into those attributes in the next lesson, right. Okay then.